All right, hi everyone. I'm Greg Peairs. I'm a research scientist at the AWS Center for Quantum Computing. Today I'm talking about the computer-aided design of quantum integrated circuits, or how we're using Julia to design quantum hardware. So some background. The devices we're designing are integrated circuits in that they're fabricated like most any computer chip, layer by layer in different materials, different microscopic patterns, on top of a single substrate like a silicon chip. They're quantum in that we want to take advantage of quantum physics, like superposition and interference, to do computation. The approach that we're taking is one among many. We use what are called superconducting qubits, or quantum bits, where the quantum part comes from the physics of superconductors. So here's a picture of one of our chips, the gray square in the middle. It's inside of a larger package. The whole thing fits in the palm of my hand. We would then close this up, put it in a refrigerator where we operate the device at a fraction of a degree above absolute zero. So that's all to say that the problems we're thinking about, some of them are inherited from traditional electronics, and many of them are specific to the design of a quantum device. So that's a quantum integrated circuit. The other half of my title, computer-aided design, can encompass a few things. In our case, one is geometry. So this is a representation of the device as 2D shapes with information about the material layers they correspond to. So in this graphic here, we have black, where we want to remove some metal from the first layer, and red, where we're depositing some other material to get basically a wire with some bridges over it. Sort of a toy example. But that's the sort of thing we would send off to be fabricated to get a real device. We also work with higher level descriptions of devices. So the schematic, which I'll say more about later, describes what are the components in the device, how are they connected. And then there's a lot of physical modeling that goes into a design. The part that I'll focus on is finite element simulations of electromagnetism. That's closely tied to both of these other two things. And I'll get into that more later. So the design cycle goes back and forth iteratively between all of these things. And ideally, you want a single tool that ties them all together. And so we've internally developed a package we've been calling Layout.jl to do that. It's now mature enough we're having discussions about open sourcing it, not necessarily under that name, hence the quotes. But if you're interested in any potential future release, please get in touch. Pending that, I'm going to focus on the problems we're solving and how we're using Julia rather than showing code. So this started out as an internal fork of a package called devices.jl from an academic group with close ties to us, a lot of the same people. But we found that if we wanted to scale up to devices that are larger than academic demonstrations with a few qubits, we identified some things that would be bottlenecks going forward. So one of these was the layout workflow itself. Designers don't want to be working directly with geometry all the time, which polygon goes where. They want to work in terms of how components are parameterized and how they're connected. So that's called schematic-driven layout. We added a nice interface for that. Another focus area has been the simulation pipeline. We want to automate as much as possible. So to that end, we developed a bunch of new geometry features, including 3D modeling to produce meshes and configurations that we can then use to call out to external simulation tools. And finally, less technical, but still very important, has been designer collaboration. As our team grows and we're building more on our own past work, we've built tooling to leverage the Julia package manager as much as possible. So a device design is a Julia project, fully reproducible. We manage a library of components in a private registry, our process development kit, or PDK. And with that, I'll zoom in on a couple of these things, starting with the schematic-driven layout. This is the idea that a designer works with some kind of abstract representation, like on the left, to produce an actual device, like on the right. So in more detail, this is a PowerPoint illustration. The designer is working in code. But they're building a graph with metadata, where the nodes are the different kinds of components. So, say in yellow, those dots are 3 qubits on this device. And then the edges are connections between them. So, this port of this qubit is connected to that port of that qubit. And it turns out that's enough information, if we're pulling all of these different components from our library, to then automatically generate the layout for the device on the right. So we're doing placement and routing based on the schematic. And so on the right, we have a microscope image of an actual device in false color to show the different kinds of components. And there's a paper, the QR code, for what we did with that. Then for the simulation pipeline, this is talking about going from a 2D representation of our device together with information about the fabrication process to generate a 3D model. We use the Open Cascade geometry kernel via the gmesh.jl interface package, and then generate a 3D mesh, which we then use for finite element simulation. The tool we use for that, we've also developed in our team. It's called Palace, which we use for large-scale electromagnetic simulations over hundreds or thousands of cores. It's not in Julia, but it's very cool. You should check it out. And what I want to zoom in on here is the meshing. So mesh in the finite element method is a discretization of space that allows us to turn Maxwell's equations for electromagnetism into a numerical linear algebra problem. And the quality of the mesh strongly affects how well-behaved that problem is. As you throw more resources at it, its accuracy, its convergence. So if you do sort of the naive thing, if you're working with a polygon-centric tool, which is very reasonable, a lot of in the end fabrication tools are going to want polygons to draw the device. If you have a nice curved wire here, these are circular arcs, but we've discretized them too early. They're now piecewise linear shapes with a ton of points on them, and the mesh wants to connect all of those points, and we end up with a lot of long, skinny triangles, which is bad. But that's not a constraint of the 3D geometry kernel or the mesh itself. You can have even curved mesh elements. So if we sort of hang on to this exact geometry information as long as possible, as well as things like the physical information about what layers we have and even design intent, we can use all of that information to make the best mesh that we can. So hopefully that already gives an idea of why we think Julia is such a good fit for this problem. It allows us to have these rich geometry abstractions with low overhead that we just carry through until we dispatch on whatever backend we want to render to, whether it's a geometry backend or this 3D simulation inputs. And of course, reasons everyone likes Julia, good performance, fast onboarding for scientists, even without a whole lot of Julia experience. As I mentioned, it's great for reproducibility and collaboration. The package manager is best in class. We leverage the ecosystem as much as possible. I'm not going to read all of these off, but I'll just finish. Thank you for everyone who's contributed to the ecosystem. Thank you to my team for making this possible, and yeah, thank you all for your time.
So we're at time. If you would like to ask the speaker a question, we have a 10-minute break, so I guess we can pass the microphone over. Or if you'd like to go to the break before the keynote, feel free to do so. Our next keynote is Andrew Fitzgibbon, who just got elected a Fellow of the Royal Society. But you have a question.
Does it output like a GDS file?
Yeah, that's the main format that we support. There are other 2D graphical formats with sort of bare bones support, like DXF, SVG, but mainly GDS.
It's open source?
Not as of this moment.
But you are planning to open source the main package?
I can't say for sure, but we're discussing it. Yep.
Okay, thank you.
Thank you. Thanks again. Oh, we have one more question.
And how do you define a good mesh to match the certain accuracy, especially in electromagnetic problem?
Yeah, so it's something that you have to test at first. So you can either benchmark against problems with known solutions or do refinement studies where you take a starting mesh and decrease the element size and see how the solution you get behaves as you do that. And then with experience, you learn which sorts of meshes are good for which sorts of geometries.
All right, so we should definitely head to the break now. We'll have the Quantum Mini Symposium in this room after lunch at 2 p.m., so definitely come back for that. Thank you again to all of our speakers.